All right, so hi guys. I'm recording another video on gravitational fields. So as usual, yeah, let's get ready and make sure that you're properly able to absorb this information. I recommend that you sit at your table and do this revision video properly lah. So just sit up straight, make sure you got everything in order. And you can head over to the website to go and get the topic notes, right? So we'll be using the topic notes as well as the syllabus learning objective. So I think quite an intuitive and straightforward chapter, as long as you go from the ground up. Okay, so a lot of things are quite in-depth, but nonetheless they build on each other. So as long as you're able to understand the earlier learning objectives, it progresses into a deeper understanding. Okay, and so this is actually a bit more intense than usual because on top of the standard learning objectives from Cambridge, I've appended my own learning objectives. So these are through the TYS, I've realized common concepts that they're testing, and I've added them in as well. Okay, so these are not officially made by Cambridge, but they've been tested so frequently that might as well just edit it. Okay, so yeah, let's use this to serve as a revision guide to gravitation. Okay, so for gravitational fields, let's quickly iterate through the learning objectives. So the very first one is just to understand the concept of a gravitational field as a field of force, and then define G field strength. Okay, so quite intuitive. Let's start on a new page. So the most important thing to understand is the general concept of a field of force. Now, this, whenever they write it so generally, right, you must also give the definition in general. So there are three types of fields in your syllabus. So you have gravitational fields, you have electric fields, and you also have magnetic fields. When they ask you to define what's the general concept of a field of force, it's written this way. It is a region of space where an object experiences a type of force due to a particular nature. So I'll give you one example in gravitational field, right? So you can define G field now. Then the logic is it is a region of space where an object, and in this case, what is the nature of the object? The answer is it has a mass. So you can write where a mass experiences a gravitational force of attraction due to the presence of other masses. Okay, so that is what a gravitational field is. Okay, then the next thing is to understand how the field lines look like and their significance. Okay, so a very straightforward thing is to draw Earth, right? And you know already that any mass will create its own gravitational field. So I'm just considering the mass in this case to be Earth. Okay, so Earth's gravitational field looks something like this. You've probably encountered this all the way back in Sec 4 even, right? And so the logic is as follows. You have these field lines and they all point towards the Earth. Okay, so towards the center of the mass. So if I were to extend these dotted lines, they all intersect right smack in the middle. Okay, so that's how you can think about these field lines. Okay, and so you must remember that there are two important things about these field lines. So two significant features. The first one is going to be the direction. Okay, and we write it this way. The direction of the field lines indicates, right, the direction of gravitational force that would be exerted on a small test mass when placed at that point. Okay, so the logic is, imagine now, right, I put a small mass here. Then the direction of the G field is just trying to tell you that if there was a small mass placed there, there will be a gravitational force like that, Fg, in that direction. Okay. So other than direction, you must also care about the separation or the density of the field lines. Okay, so the closeness of the field lines. So the other thing is the concentration slash density slash closeness of field lines. Now, these all mean the same thing, and the logic is just the closer the lines are, and the stronger the G field. Okay, so on top of just understanding the concept of a gravitational field, they also want you to know what is the gravitational field strength. And that one is just the definition. Okay, so it's quite basic. So gravitational field strength refers to what? Okay, then here refers to the gravitational force acting per unit mass. Okay, and remember, right, gravitational field strength, right, is always defined at a point within the gravitational field. Okay, so it refers to the gravitational force per unit of mass acting on a small test mass placed at that point in the gravitational field. So they are trying to say this law. If you have a mass m, and then you put the object there, right, a small test mass, the gravitational field strength at that point, G, is equals to Fg per unit of mass. So you probably already know the formula. It's Gmm over r squared divided by m. And now remember, this m will cancel this m, so you get Gm over r squared. So a very common question I get from a lot of the students is, well, which m remains? So what is the m that is left behind? And the way to remember it is the m that is left behind in the equation is the mass that created the field strength. Or let me write, created the gravitational field. Okay, so yeah, that's how you can think of G field strength. So we're done with learning objective. Okay, then the next part, they ask you to recognize the analogy between qualitative and quantitative aspects of G fields and E fields. Yeah, I'll circle back to B later, so no stress about this. But I would say the following, if you're studying gravitational fields, you might as well also study electric fields together because you'll see a lot of similarities and they are both very analogous to one another. In other words, what you study in G field, right, you just need to tweak it a little and you end up with electric fields, the same concepts there. Okay, next thing. So you also get C. They want you to know how to use Newton's law of gravitation. Okay, so let's do learning objective C now. So you must remember what is Newton's law of gravitation. So I'll write it as Newton's law of gravitation. And the short form, right, I always write in my notes as NLG. Okay, so you can't use this in exam. Make sure you spell out in full. But for revision purpose, if you ever see me write NLG, just means Newton law of gravitation. Okay, it basically says this: the gravitational force of attraction between any two masses is directly proportional to the product of the masses and inversely proportional to the square of their separations. Okay, and now important now, look. They always specify that Newton's law of gravitation, when Newton first discovered this, right, he did some complicated calculus, some math, some differentiation and integration, right? And he realized, right, that this formula only is true if the masses are point masses. Okay, so this is important. Now, they love to test this as one of the follow-up learning objectives. Okay, so I'll show you what I mean. But let me write out the formula first to represent this mathematically. So basically, Newton's law of gravitation is trying to say this. Gravitational force is directly proportional to m1, m2 over r squared. Okay, and you already can see, actually, based on direct proportion, right, I get this. K, m1, m2 over r squared. And the nice thing is, based on direct proportion, you know that there's some constant of proportionality. Now, this constant, right, we don't write it as K anymore. You're actually given the constant, which is G. And this is given in the data booklet. The value is 6.67 times 10 minus 11. Okay, so no stress about this one. Okay, so yeah, that's our second formula here. Okay, and let me help you visualize this. Okay, so let's take a look at the following. Let's say I have one point mass m1 and another point mass m2. Then I'm basically trying to illustrate Newton's law of gravitation here. I'm saying that the gravitational force that each of them experiences, so let's call this Fg, 2 on 1, is going to be also acting on the other mass, Fg, 1 on 2. These forces are proportional to the product of the masses here and inversely proportional to the square of the distance that separates their centers. Okay, so this is called the separation. Okay, so you must remember, F is proportional to m1, m2 on r squared. Okay, so this is this learning objective. Done. Okay, now next thing that you must remember also is one of the additional learning objectives. Now you go and check the TYS. They actually test Newton's law of gravitation and why you can apply it on planets, even though planets aren't point masses. Okay, so I'm going to cover one of the additional learning objectives now. Now, this is a very common question, so notice the following. Even though I have planets like this, right? And these planets, right, are not point masses, we can still apply Newton's law of gravitation. Now, you might be wondering what the hell a point mass is. A point mass is. So let me define a point mass. Okay, a point mass is one whose mass only occupies a single point in space. Okay, and this basically is trying to tell you, oh, there is no radius, there is no volume. It just basically takes a single dot in space. Now, if you have learned vectors in H2 math, you would already know what a point is. A point means. Okay, a point, it doesn't have any space that it occupies. So that's why we call it a point mass. Now, in real life, do we have such things? No lah, there are no such thing as point masses. Okay, and so how come we can still apply Newton's law of gravitation here? So it's a very common learning objective. Now, I want to help you visualize this. And so the reason, right, is because the dimensions of the planet are so bloody small compared to their separation. So I'm trying to help you visualize with this drawing one. Okay, so let's imagine I draw a line from the center of this to the other center of this. Now, in real life, the logic is these masses are not actually point masses, which means the center of gravity, right, could actually have been somewhere, right, that is not in the middle. And think about it, in real life, this makes a lot of sense because the planets don't have a uniform density, right? So there might be different compositions of the rocks that form up the planet at different points, making the center of mass, right, not right smack in the middle. It could be anywhere else. For example, the true center of mass, right, for this guy could be somewhere here or somewhere like here and here. And notice that, well, that makes the R slightly different, correct? So it makes the R slightly different. But is it significant or not? The answer is no lah. Like you look at the picture, right? You see the black line and the blue line. There's barely any difference. And the reason why there's barely any difference is because the separation between the planets, we'll call this R, is so much bigger than the dimensions of the planet. And so therefore you can just say, okay, we approximate these planets as point masses. And now I do want to just build your understanding a little deeper, and I'll actually compare the values for you. So let's take a look at the diameter of Earth. Now notice the diameter of Earth is quite big, it's 12,000 kilometers. And let's also check out the diameter of the moon, it's about 3,000 km. Now you might think that these numbers are quite gigantic, and I agree with you. But if you take on it, if you take on the perspective of a relative size, then compared to the separation, right, they are super tiny. Okay, so remember these two numbers are 12,000 km, 3,000 km. Then let's take a look at the separation between Earth and Moon. And wow, it's way bigger, 384,000 kilometers. So I hope you agree, actually, the separation is so much bigger than the dimensions of the planet that the dimensions of the planet don't really matter. So we can just treat the planets as point masses. So a common question is why can we approximate or use NLG on planets even though these aren't point masses? Okay, and then the thought process is just this lah. Okay, so the dimensions of the planet, and when I say dimensions, right, you can think of it as like the diameter of the planet is much smaller than their separation. Okay, hence, we can approximate these planets as point masses and thus apply NLG to them. Okay, so yeah, we are done with this additional learning object. Okay, I hope that was clear. Okay, so done with this and this. Yeah, Newton's law of gravitation. Okay, then now the next one, D is extremely easy. So they then test you about Newton's law of gravitation. They want you to derive gravitational field strength. Okay, so we can do learning objective D and E together. It's quite intuitive. Okay, so for learning objectives D and E, let's do this. Okay, so remember, right, for gravitational field strength, G, it refers to the gravitational force acting per unit mass. Okay, and remember, right, it's always at a point in a G field. Okay, so then by definition, we can say this. G is the gravitational force on a unit mass. Okay, so basically per unit mass. And then you just submit now. So by Newton's law of gravitation, all right, here, it's going to be G m1, m2 over r squared divided by m. And which m do we divide by? Is the mass that we're putting on the gravitational field. So in the context of my example just now, right, we divide by the point mass where we are putting the additional mass in that gravitational field. So for example, if we are looking at Earth and this small unit mass, or this tiny mass that we're putting here, then I'll be writing it a little different, something like this. Instead of m1, m2, let me write it as me, the mass of Earth, times the other mass that I'm placing in the field. Then I just divide by Zn. And I end up with this. Okay, and so this is the gravitational field strength at Earth's surface, okay, or anywhere in the gravitational field. So in the context of this example, the R, right, if I want to find the gravitational field strength at this point, then I'm considering this R. Okay, so that's the thought process for this. Awesome. Okay, so yeah, we are done with this learning objective. Now, to make it more general, then I will remove the ME. Okay, so I can just say, oh, it's the mass of the guy creating the field. So once again, I'll also replace this ME with M. Okay, so yeah, that's how you derive out gravitational field strength. Okay, so going back to this, we're done with learning objective D. Now, the next part, right, they ask you to be able to recall and apply this equation. Now, this one is just an intuitive, like you have to do questions, right, to get it. Okay, so for learning objective E, they're basically saying, can you use this equation to solve questions? Okay, and honestly, I feel like even if you read this now, it won't really help you develop a skill. You kind of need to do practice questions. So once you're done with this video, go and try some questions about this. Okay, so you can find it on the website. Okay, next, let's then go and solve F. So for learning objective F, they want you to be able to show that near the surface of Earth, the G field strength is approximately constant. Okay, and then the second part of this learning objective is that it's equal to the acceleration of free fall. Okay, so let me start on learning objective F now. Okay, so now I want you to think of it this way. Look at Earth here. And then let's consider, right, when we are really close to the surface of Earth. So consider this point. Okay, and consider, right, when we're near the surface of Earth, we are still around the same area. Okay, so notice, right, this height is very, very small relative to the radius of Earth. Okay, so that means that actually there's very little change in the gravitational field strength. Okay, so that's why, right, the gravitational field strength is approximately constant near the surface of Earth. Now, the best way to think of it is like this. Let's imagine, right, we're right smack at the surface. So let's call this G surface. Now, G surface is just going to be Gm over r squared. Okay, and then what about some small height above the surface of Earth? Let's call this G at height, h. Then the logic is about Gm over r plus h squared. Now, why r plus h? Because that's the total distance from the center of the Earth's mass. So this will be r plus h. Okay, so yeah, then notice these two values are going to be super similar to one another. Now, what's the logic? Well, because this height is generally much, much smaller than the r. So if you go and calculate the difference between G surface and G at height h, then you barely see any difference. Okay, and that's why we can say the G field strength is approximately constant. Now, to give you an example, I can think of the tallest building on Earth. Okay, so okay, I'm not sure whether it's still the tallest building on Earth, but let me go and search up the Burj Khalifa. Okay, so the Burj Khalifa is actually one of the tallest buildings on Earth. It's a skyscraper in Dubai. And notice, right, its height is actually not very tall. It's only about 830 meters. Now, okay, when I say it's not very tall, I'm trying to say in the grand scheme of things, it's really, really quite tiny. This is less than 1 kilometer. And remember that actually Earth's radius is about 6,400 km. So if I go and add on just about 1 km more, right, it barely makes a dent, it barely makes any difference to the gravitational field strength. So we can say near the surface of Earth, the G is almost constant because this H relative to R isn't much. Okay, so we can say this. Near the surface of Earth, H is much smaller than R. So we know G is approximately constant. Okay, so that's what they mean by gravitational field strength is approximately constant. Wait, this is really important. Whenever this is the case, you can approximate change in GPE as just mgh. Now, how come you can just do this? The reason is because mg is approximately constant. So then if you want to find the change in GPE, it's just going to be taking like the force here as a constant. Okay, so I want to help you understand why you can do this. So let's do the following. The change in GPE, and let me be specific, is near surface of Earth. We actually define it this way, is the work done, okay, against gravity. Okay, and you can think of it as the work done against the weight. And so then I hope you agree, right? It's the integral of the weight with respect to R. Okay, which is the integral of the formula for weight is mg dr. And I want to just basically reiterate the g here is approximately constant, which means mg is approximately constant. So how do you actually integrate a constant with respect to R? I hope you agree, right? It's just going to be like for example, integrate k dx, where k is a constant. You end up with kx plus c, right? Where c is some arbitrary constant. So let's ignore the additional constant. Let's just imagine when you integrate a constant, you just times the value here, right? So I'm going to get rid of this. And so I hope you agree, oh, therefore this is just mg delta h. And that's the change in GPE. Okay, so remember, when you are close to the surface of Earth, and the G field strength is therefore approximately constant, you can just estimate changes in GPE as mgh. Okay, so we are done with the first part of the learning objective. So let me just take the first half. Now, the next thing to understand is also why the G field strength is approximately constant, and more importantly, rather for the second objective, why it's equal to the acceleration of freefall. Okay, so let's do this. So the second part of that objective is why is acceleration of freefall equals to g. Okay, and this one's actually quite intuitive. You've already learned it in Sec 4. So the understanding, right, actually applies from the concept of free fall. So do you really understand what free fall is? If we say free fall, we are basically trying to say there are no external resistive forces. Okay, so that's what it means to fall freely. So in my head, I'm always reading it as an object is falling freely from any resistance. Okay, so then very easy already. Consider a free body diagram. If I now tell you that you have free fall, means the only force acting on the object, right, happens to be the weight. Okay, so there's no air resistance, there's no drag, there's nothing. It's just weight. Then from there, right, I hope you agree. Resultant force is the weight. Okay, because there's no other force now. So you have ma equals to mg. And this a, right, is called the acceleration of free fall. Okay, then you realize, oh shit, I can just cancel m. And so therefore, acceleration of free fall is just g log. Ta-da, done. Okay, yeah, so we are fully done with this learning objective. Okay, next. So then they are starting to test you about the concepts of potential and potential energy. Okay, so for this one, right, I'm just gonna quickly run through the concepts as well as the definitions. And if you really understand this, I think it's still not enough. You must still practice questions. Okay, so let's quickly define gravitational potential. Okay, let me first see. Yeah, gravitational potential. Yeah, and okay, honestly, I know the syllabus objective didn't write it, but I don't like to study potential alone. So you should also go and study what is GPE. It will help you build an in-depth understanding. Okay, so let me go and quickly solve G and H together. Okay, so I'll do one section on GPE. Okay, so would encourage you to sketch this out to build an understanding on. Okay, so let's do the following. Suppose, right, I have two masses, M1 and M2. Okay, so then what the hell is the GPE of this system? So let's first define gravitational potential energy. So let's do it this way. Gravitational potential energy of a system of masses. And wait, don't panic about this phrasing. A system of masses here, I'm basically just saying multiple masses. Okay, and so it refers to the work done by an external agent in driving these two masses from an infinite separation to their current separation without a change in KE. Okay, so that is the definition of GPE. So I'm basically saying the GPE of this system is the work done when I want to drive these two masses from their originally infinite separation. So try to help you visualize this. Let's imagine they were originally separated by a super far distance. Something like this. I always draw this blurb. This blurb is like saying, oh, there's some infinite distance between them, right? To their current separation. And it's from the center of the masses. So let's say from the center here to the other center here. Okay. Let's call this R, right? So it's the work done by some external agent, okay, to ensure, right, that they don't change the KE. Okay. So first of all, I'll show you why you actually need to do some work. Okay, and the reason, right, is because of this condition here. You don't want them to change KE. Okay, so now think of it this way. If you look at the top diagram and you don't do anything to the masses and you just allow them to get closer and closer, notice that there will be a gravitational pull on both of them. And if you don't supply any external force, what will happen is both of them will experience acceleration. So both of them will actually increase kinetic energy as they eventually reach this separation. Okay, so to make sure, right, that you don't have a change in KE, then notice you must go and do an external force that is opposite to FG, right? So that it doesn't allow it to accelerate. Basically, it moves at a very, very small, zero, almost zero speed. Okay, and there's no change in KE. So you bring them all over to their current separation. Okay, so yeah, that is the definition of GPE. Okay, so we can say the following. GPE is just the work done by the external agent. Okay, that's the key idea. You die must get this. Okay, then what is the work done by the external agent? Well, I hope you agree, right? It's just the integral of the external agent with respect to the displacement. Okay, so now notice, this is where it gets fancy. What is this external agent's force going to be? So look at this picture real carefully. If you don't want this fella, right, this mass M2 to accelerate, then I hope you agree, you're trying to say, oh, resultant force must be zero. So then we know that the external force must be equal in magnitude to Fg, but it must act in an opposite direction. Okay, fantastic. So then, this is integral of Fg. Yes. Okay, and remember, right, it's opposite direction, so there's a minus sign. So you can actually say, oh, it's the integral of minus Fg ds. Okay, and so what the hell is S? S, right, is the displacement. So if you are dragging it from infinity to their current positions here, then this is the direction of S. Okay, and so then the GP of a system of masses is just a minus GMF over R. Okay, so yeah, that's it. There we go. And this is honestly the easy problem lah. Okay, so why? Because in your syllabus, right, they could actually give you more than two masses. And yeah, let me quickly do a note on this. So what if there are multiple masses? How to find the total GPE? So I'll give you an example now. Suppose I got mass M1, M2, M3. This is M1, M2, and M3. Or then very easy, if you want to find the total GPE, then actually, right, you must just remember this. GPE is a scalar quantity. Energy is a scalar quantity. There's no direction associated with gravitational potential energy. Then, based on that, if I just want to find total energy, right, I just sum all the GPEs. Okay, so this sigma here, it just means the sum of. Okay, so I want to find the sum of GPE associated with mass 1, mass 2. So I'll call this R1, 2. Then I'll call this R1, 3. And then I'll call this R2, 3. Then quite easy already, because I just need to do GPE 1, 2 plus GPE 1, 3 plus GPE 2, 3. That's how you can get the total GPE of the system. And low-key, quite easy lah. It's just G M1, M2 over R12 with a minus in front. Then I basically add up all the GPEs associated with the system. Okay, so this will be a minus G M1, M3 over R13. Okay, and then lastly, plus minus G M2, M3 over R23. Yeah, then you'll realize, right, oh, actually it's just the sum of all the GPEs. So it's minus G M1, M2 over R12 minus GM1, M3 over R13 minus GM2, M3 over R23. Okay, so yeah, that's how you can find GPE of a system of masses. Okay, so this one can come out in exams and usually it's the killer question. Okay, but I hope you realize it's quite easy. It's just GPE is a scalar, so just add it as a scalar. Then you're done. Okay, so we are done with gravitational potential energy. Now we actually have to move on to a harder concept, which is gravitational potential. Okay, so I'll go a bit slower on this. Let's draw a line here. Okay, so I'll try to give you a bit of understanding of why they even came up with this. Okay, so the logic, right, is you know how to find the GPE of a system, right? Okay, but what if you are just looking over at changes per unit of mass? Okay, and so why would that even be important? So imagine, right, this is Earth. Okay, I'll build the motivation behind why we study this thing in the first place. So let's say this is Earth. Okay, and then suppose I got one satellite here. So satellite S1. Okay, and then look, I do some calculations, I figure out that as I drag S1, right, closer and closer and closer, I know that, okay, I'm going to have a change in GPE as I bring it from position A to position B. I know I have some associated change in GPE. Okay, and so then you realize, wow, if I change the mass of S1 to any other mass, then I need to do my calculations from scratch again. So for example, right, this is the first case. And now imagine I tell you, okay, I put a heavier satellite now. So the satellite now becomes bigger, something like this. In this. Okay, so same, it's a new satellite with constant mass. So we'll call this S2 lah. S2. And then I bring it over from position A to position B, right? Then the logic is, wow, do I need to go and calculate everything from scratch again or not? Right? You realize, wow, it's a lot of repeated work. And think about it, in real life, right? If you are, let's say you are the owner of SpaceX, so you're Elon Musk, then you want to shoot up a satellite, right? You're going to shoot it up to the same orbital position, right? So you're basically going to keep doing changes of these particular positions very frequently for different satellites. Then the thing is, you need to keep doing the calculations again, man. Like, what's the point of doing the calculations so many times? The only difference is the mass of S2, right? So that's where the scientists all discovered, oh, why not we just do the changes in GPE per unit of mass? Then I know, right, if I can drag one satellite from one position to the other position, and I know its value, right, I know its mass, I can basically use proportional and calculate if I were to bring up a heavier or a lighter satellite, what would the GPE be? So that's the motivation behind why they created or they invented this concept of gravitational potential. Okay, so gravitational potential now, let's write the symbol GP, gravitational potential, GP, is represented by phi. Okay, so this is what it looks like. Okay, gravitational potential. And we'll define we'll define this concept here. So the gravitational potential is very similar to the GPE definition, refers to the work done by an external agent. Okay, and this one important. So remember, you just find it per unit mass. Okay, in driving a small test mass from infinity to that point in the field. Okay, so and remember, right? So everything's always defined at a point in the G field. Okay, so it's the work done by an external agent per unit of mass to drive a small test mass from infinity to that point without changing its kinetic energy. So that's what phi is all about. Okay, and I'll try to help you visualize this again. So imagine, right, you have Earth here. Okay, so the concept is trying to say, okay, if you want to find the potential, right, at some point, suppose you want to find the potential at this point here, then the potential is just equal to the work that you would have done to drag it from infinity, let's call this infinity here, to this point. Okay, so to point A, without changing its KE. Now then look, if you put any unit mass here or any mass in general, the idea is the same concept applies. It will be attracted to Earth. So there'll be a gravitational force. And if you just let it move over with this force, right? Then what happens, right, is naturally, it will speed up. It will accelerate, so its KE would increase. Okay, so then how must you apply an external force to prevent it from accelerating? You can probably already visualize that, okay, the external agent must be directed in the opposite direction with an equal magnitude to the gravitational force. Okay, yeah, then I think quite easy already. So you can probably figure out, well, the gravitational potential, phi, okay, let me write it here. Phi is just going to be work done by external agent. Okay, and the intuition is you need to do this work again so that you do not change the KE of the object. Okay, and remember, it's the work done by external agent per unit of mass. Okay, so yeah, then I think the rest is quite intuitive. The work done by the external agent per unit of mass happens to just be the integral of F of the external agent ds over the mass. And S here, right, is the displacement. Now, if you're wondering why work done is the integral of force with respect to displacement, this one is back in your earlier chapter called work, energy, and power. Now, the easiest way for you to remember, right, is from your Sec 4 foundations. Work done here is just force times distance traveled in the direction of the force, which is also the same as saying, oh, you find the area under the force distance graph. So that's why it's integral of F external ds. Okay, and then logic is quite intuitive. This is going to be negative Fg ds over m. Okay, and here's the very, very cool part. This becomes Fg over m ds. Okay, and so what's Fg over m? Easy. We actually defined it just now, right? It's just negative g ds. Okay, and the ds here, right? The s, right, is just the displacement. And notice, right, we can also replace it with like the change in r, which is the separation, right? So the original r, right, from Earth to this point is r. And then as you're moving the mass over, the r changes to this smaller r. Call this r prime. So if you can also just replace the s here with r. Okay, and then you end up with this. So you don't need to know the calculus behind this, but if you want, you can prove it out. It's well within your H2 math already. Okay, but in our syllabus, you don't actually have to remember how to do this. You just need to know the final formula. So the answer is going to be minus gm over r. And this is fine. Okay, so yeah, that is the potential at a particular point. Okay, so quite important, you have to remember, right, that the potential is just going to be the area under the G field graph, right? And that's given here. Okay, so yeah, I think we are done with this concept. There we go. So gravitational potential is the work done per unit mass in driving a small test mass from infinity to that point. Next thing, they also want you to remember this formula. So that's it, done. Okay, yeah, so let's check. Before I go on to these other two things, okay, then I also should cover the additional. Yeah, okay, these additional learning objectives which come out so frequently. Okay, so my next additional objective is I need to be able to explain why potential and potential energy are always negative. Okay, then this one, right, you can check the TYS also, come out like a lot. Okay, so let's quickly write a template for this. So let's do this here. Okay, so look, for the GPE one, right, it's intuitive. You can think of it this way. GPE is the work done by an external agent in driving the system of masses from infinite separation to their current separation without a change in their KE. Okay, so then try to visualize it this way. So let's say this was the original infinite separation. And then you have mass 1 and mass 2 here. Then if you don't do anything, right, both of them will be attracted to each other. Call this F1 and F2. Then the idea is, if you want to find the GPE, think of it, right, as the work that you must do to make sure they don't change K. So then the external agent, right, will be directed this way. There we go. Okay, so F external. Then notice, right, look, the external agent must act in an opposite direction to F2, and you're dragging it from infinity to their separation, which means the displacement that you're dragging the masses is opposite in direction from the external force. So when you have force and displacement in the opposite direction, the work that you do is negative. Okay, so this is leaning on your foundations from work, energy, and power. If force and displacement are in opposite directions, work done is negative. Okay, so you can say the following. Since the gravitational force is always attractive, then we can say the external agent must be in the opposite direction for its KE to remain constant. Okay, then external force is always opposite in direction from displacement. So work done by external agent is negative. Okay, and you must also state this one last sentence. In addition, we define the GPE to be 0 at infinity. Okay, so yeah, this is the thought process for why GPE is always gonna be negative. Okay, so then look, we have done this already. Why is GP always negative? Now the follow-up, right, is can you explain why GP is also always negative? Then the answer, right, is more or less the same thing. But now instead of thinking of a system of masses, you consider, right, just potential. So for potential, you only need one mass. So let's call this M1. Then you're trying to drag a unit mass or small test mass from infinity to, let's say, this point. Okay, so same idea, this is infinity. And you don't know what mass you're placing here, but it doesn't matter because it's always per unit of mass. So dragging it from infinity to their current separation, which could be like here, right? So this was the original infinity. Okay, and then the logic is same idea. If you put any mass here, it will experience a gravitational force of attraction. Okay, so the external agent must be in the opposite direction. Okay, so yeah, we can also write another explanation. So why is GP always negative? And same idea also. The gravitational potential is always negative because the external agent's force must be directed. Okay, wait, let me write it this way. Because gravitational force or field strength is always attractive. Okay, so hence, the external agent must be directed opposite to the FG, okay, or the gravitational field strength, okay, in order for KE to remain constant. Okay, so thus, the work done by the external agent per unit mass is always negative. Then also write this, in addition, gravitational potential is defined to be 0 at infinity. Okay, so that's the thought process for this. Okay, so yeah, let me just make my notes a little neater. So yeah, the top one explains why gravitational potential energy is negative. The bottom one explains why GP is always negative. Okay, and I think quite easy lah. Okay, they are very, very similar to one another. Okay, so I'm done with this additional learning objective here. Okay, then before we dive into like orbits and stuff, circular motion, you also must be really comfortable with sketching these GR, phi R graphs, as well as understanding the null point. Now, I will show you the one mass problem and then the two mass problems. And I'm quite sure, right, when A-level tests this, and even your prelim exams, when they test this, it's often going to be the case that they test you two mass problems. Okay, so let's quickly do this real quick. Okay, so here, consider the one single planet. Okay, let's call this Earth. Okay, then how will its gravitational field strength graph look like? So the answer is, okay, it could look like this. Okay, wait, let me draw a line from the surface. Because you only expected to know, right, what the G field looks like past the surface, past R here. Okay, and then let's call this R. Okay, R is the radius of R. And then this small r is just the separation, right? So from the center of mass of the Earth. Okay, so big R is radius of Earth. Small r is separation of that point from the center of mass of the Earth. Okay, so how will this graph look like? Now there are two valid answers. Okay, the first answer, right, is this. You have whatever value this is, and then it drops down like that. So this is proportional to 1 over r squared graph. Okay, now it could also have been this though. And why? Because G, right, is a vector. Okay, so gravitational field strength is a vector. So whether it's positive or negative just depends on your sign convention. Okay, so if I draw it as positive, right, then I'm just basically saying this. If you put any mass m here, right, then I take the leftwards to be positive. Okay, because you know, if you put a mass there, right, the gravitational field it will experience is a pull to the left, towards the Earth. Okay, so then down here, right, it's positive if you take positive to be the direction towards Earth's center. Okay, but it could be also negative if you took right as positive like that. Then, but the shape is the most important part, which is just a 1 over r squared. Okay, and you also know this value. Okay, so at the surface of Earth, the gravitational field strength is just going to be 9.81. Okay, then yeah, that is pretty much how you can sketch this graph. Okay, then how about potential? How does potential look like? Potential, right, is a different one. Potential is a scalar quantity. Okay, so all values of gravitational potential, phi, is always going to be negative, right? And that's what we discussed just now. Gravitational potential is always negative. So then we know the graph will look like this. Okay, there we go. Should look like that. Okay, and this shape is no longer 1 over r squared. It's proportional to 1 over r. Okay, and why is this the case? Because phi is minus gf over r. Okay, so that's how you can think of G graphs with respect to R and phi graphs with respect to R. This is for single mass problems. Now, this is your basics lah. Okay, now we do a little bit more advanced stuff. So what about systems? Okay, so let's call this a phi R and GR graphs for two masses. This one is the common one you see lah. Now, honestly, not difficult. Okay, but I show you how to think about it. It's the most important thing. You must know how to think about the question. Let's consider mass of Earth and then mass of Moon. Okay. Then we'll draw two graphs. One is the G field strength like this. And then the other one, here, this is going to be phi. So this is GR, this phi R graph. Now, must remember how and must know how to think about this problem. Okay, let me just drag this up so I got a bit more space. Okay, so then think about this line in between both the masses. Okay, then look, you're only going to consider past the radius of the planets, like that. Okay, now don't panic, don't try to immediately draw the graph. Okay, that's what most people do, then they die. Don't do it that way. I would rather you think of the gravitational field due to each mass first, then you draw the combined effect. Okay, so I show you what I mean. So consider, right, this point here. If you put any object or any mass here, now it would experience a pull to the Earth, and this is G Earth. And then it will also experience a pull to the Moon, which is G Moon. Now notice, right, that G Moon and G Earth are vectors, and they're pointing in opposite directions. So this means the gravitational field due to each of them, right, will have opposite signs. Okay, so then your job right after that, right, is just to figure out how does the G field strength graph look like based on Earth. Okay, and so for Earth, right, notice along this path here, along this journey here, you're basically moving further and further from Earth. And you know that the gravitational field strength, right, as you go this direction, it'll be weaker and weaker and weaker. Okay, so now let's be normal people. Okay, when I say be normal people, I mean you set a positive direction. Okay, and the default thing that I do, right, is I'll just say take right as positive. Okay, so then consider this. Gravitational pull to the Earth is going to be to the left, right? So then the G field, right, because of Earth, it'll be towards the left, which is negative. So how does the G field graph look like based on Earth? Then the answer is this. You draw a very negative value first, and then you slowly decrease to 0. So the asymptote is 0. And let's call this G Earth. Okay, fantastic. Then how does G Moon look like? So straightforward, G Moon I'll draw in blue. Now notice, right, the G Moon is to the right. So you expect positive values. Okay, and same idea, it will also vary with 1 over r squared. So it will look something like this. Okay. And now notice, important. You want to make sure, right, that the G Earth, right, is bigger than G Moon at the surface. So see this value, right? This is much bigger than this tiny bit. Now, how come? Because the Earth is more massive. Okay, so the Earth is bigger than the Moon, so the G field of Earth is going to be way bigger than the G of the Moon. So this is G Moon. Okay, then finally, if you're forced to sketch this in exam, they usually won't ask you to draw G Earth and G Moon. They'll just ask you to draw the resultant. Then the resultant is damn easy. You just need to add up the combined impact of this. So you want to find G net. So in my head, I'm saying this, okay, G net is just GE plus G Moon. And they're in opposite directions. So when you add up, right, they'll actually cancel out one another. So you end up with this very nice shape. It looks something like, okay, wait, let me draw it in red. Okay, so this is the G net. Like that. Okay, wait, let me draw a little nicer. Okay, so this is G net. Okay, so yeah, this is how you can think of the problem. Whenever they ask you for field strengths, draw the individual field strengths, then you combine to get G net. Okay, and look, you already probably are glaring at this. This here has a name. Notice that at this exact point, the net pull is 0. It has a name. This is called our neutral point. Okay, so quite intuitive. Then now let's consider drawing the phi graph. Now for the phi graph, right, I'm going to first say that you actually know one very important result already. Okay, so you know the important result. Let me write it here. Okay, let's do this relationship. So phi, right, based on what I've taught just now, phi is your gravitational potential. It's going to be the integral of minus g dr. Okay, and then look, the phi is the gravitational potential, right? Is the area under the GR graph. Now, I want you to think of it the other way. What about if I want g? Can I do the opposite of integration? Can, right? I can just do the differential of this. So then g is just negative d phi dr. You just basically do the opposite of integration and you get this. Okay, and so this is quite important because I'm trying to say, look, at this point, right, where my G was 0, okay, when my G was 0, then actually, right, my d phi dr is going to be 0. Okay, which means I have 0 gradient. Okay, so 0 gradient here. So then I'll draw a dotted line like this. There we go. Okay, and I expect this. This is my neutral point. My gravitational field strength here is 0. So I expect, right, to have a flat graph here. Okay, and remember, I shouldn't have any negative values actually. There's nothing wrong with my graph, but I should flush this whole part up. Because remember, right, all values of potential are negative. Okay, so then once again, when you encounter a question like this, I would really, really recommend you draw the potential due to Earth alone first. Then after you draw the potential due to the moon alone, then you draw the combined effect. Okay, so let's draw something like this. So for the potential of Earth, it's always a negative value. There are no more positive values because this is a scalar. Give it out. Why is it like that? Okay, scalar. So if it's a scalar, right, then you know, okay, there's no opposite signs. They're all negative. Okay, so for gravitational potential of Earth, it will follow this shape. Okay, let me be consistent. Okay, I'll use black. Right, so G Earth is black. I also make phi Earth black. Like that. Okay, and then let's draw phi moon. Okay, so what does phi moon look like? Phi moon, same idea, right? There's some potential here that starts from a smaller value. Okay, why smaller value? Smaller in the sense of the magnitude, right? So it's less massive. So then the magnitude of the phi at the surface is going to be smaller. So I'll draw something like this. Yeah. And so that's the idea behind this. Okay. Wait, then take note. Yeah, yes. You must make sure, right, that your you must make sure, right, that your net potential. Okay, so let's consider the I should draw it in blue. So for the moon's phi, right, it should be the blue one. Okay. Then I'll color code it to match the above. Okay. So this is phi moon. The black line was phi Earth. So if I want the net, right? So phi net. It's just going to be phi Earth plus phi moon. Okay, now that you have this, then you realize, right, actually to get phi net, I just need to sum the black line with the blue line. And I'll end up with this shape. Okay, so just like that. Okay, wait, let me draw a bit nicer. Yikes, sorry, one sec. Actually, okay, hold up. Yeah, okay, and I want to emphasize one thing. You see at this point, right, the gradient there must be 0. Then you just shift it down. Okay, wait, some skill issue here. Okay, so you get something like this. Okay? So take note, the gradient here, right, must be 0. Okay, and so why is it 0? Because there, when G was 0, which is here, G is 0, then the gradient of the phi r graph should also be 0. Okay, so honestly, not a very neat line. Let me make it a bit nice. Okay. There we go. Yeah, and so here, this is the null point. Okay, and notice, right, this is a maxima. So yeah, because the gradient is 0 there, so it's a maxima. Okay, so this is phi net. Okay lah, perfect lah. So yeah, that's pretty much how this is done for this learning objective. Okay, so you're comfortable sketching GR graphs, phi r graphs, and you understand the null point. Okay, so not too bad. Now, before I go over to satellite energies and Kepler's law, I also want to talk about escape velocity and also the minimum energy to leave a planet and the minimum energy to crash to the planet. Okay, so this one, right, same idea. You need to first understand escape velocity. Okay, so I'll do one entire section here. So let's write this. So what is escape velocity? And how to calculate it? Okay, so we'll do the simple case first, where it is talking about a single planet. Okay, so no two masses, just one mass. Consider this. Let's say, right, you have planet Earth here. And then you're trying to figure out, right, what is the minimum amount of energy required for this fella to basically leave the entire of Earth's G field. So I'll define it this way. So the escape velocity is the minimum energy required to fully leave the gravitational field of Earth. Okay, and I should make it a bit more general. If I say escape velocity, right, it could be for any planet. It doesn't always have to be Earth. So let me rename this to planet. Then the logic is the minimum energy to fully leave the gravitational field of the planet. Okay? Then, okay, think about it. You need some minimum energy, right? So what kind of energy are you going to convert? Okay, that's the best way to think about it. So the thought process should be you lose KE and then you gain GPE. Okay, so think of it this way. The object must lose KE in order to gain a GPE and escape the G field. Then also another thing to remember is this: to fully escape, then we want to reach where? Okay, so think about it. The answer is infinity. Okay, so we want to reach infinity because we are fully free already from the pool. So then from there, it becomes very easy, which is this loss. Yeah, I should write this out. And by the way, when you present an exam, you must derive from scratch. Okay, so you must say something like by PCE, principle of conservation of energy, right? PCE. Then the loss in GPE equals to the gain in, sorry, my bad. The loss in KE equals to the gain in GPE. Okay, so then the next thought process is, well, what is the loss in KE? Now, the loss in any value is going to be the initial value minus the final value. Okay, so that's the loss in KE. And that will be equals to the gain in GPE, which is the GPE final minus initial. Okay, so from there, quite intuitive. You just need to sub in the value. So if you want to find the minimum energy, right, then you can think of it as, the object will lose all its kinetic energy. Okay, so initial KE is just going to be half mv squared. And because you want the minimum speed, then you say, it lost all its KE. So the final KE when it reach infinity, right, is going to be 0. Okay, and then that will be the final GPE. And think about it, when you reach infinity, your final GPE is 0. Then you must minus the initial GPE. And the initial GPE of this mass is just going to be GMM over R. Okay, and remember, right, this is a negative already. So GPE itself is always negative. So that's why it looks like that. Okay, then quite easy, right? Because notice minus minus become plus. And then you get half mv squared. Okay, and m is the small mass. This big M, which is this guy, is the mass of the planet. Okay, so what can you cancel? You can cancel the small m. Okay, so cancel this small m across. And then you can solve for v. So v is just going to be 2gm over r square root. This is called your escape velocity. Yeah, so you must be able to derive this from scratch. So let me mark that off now. Yeah, know how to derive escape velocity. Done. Okay, then the next part, question 8, also very common. They ask you, right, how do you find the minimum energy to leave a planet? And the minimum energy, right, when you fall to the planet. So this one, right, is actually the harder variant of this kind of question. Okay, so the harder variant, right, usually is involving two systems. Right? So I will draw out a two-system problem for you. So consider the mass. Consider the Earth, and then consider the Moon, something like this. Okay, then consider how the phi graph will look. Okay, and then let's suppose the phi r graph, right? You already know that it will look like the combined graph, right? Will look like the inverse U shape. So what I mean by this is, based on our drawing just now, right? You know that it will look something like this. Right? Okay, then remember, right? This point is damn significant here. This here is called the null point. Okay, so die must remember this. Okay, fantastic. Then let's just say, right, this is, okay, let's just consider this A, minus A. Okay, and then let's call this B. Okay, then let's call this C in blue. Okay. Okay, so minus B, minus A, and minus C, right? These points. Now, the common question they will just ask you is, what is the minimum energy required to send an object from Earth surface to the moon? Okay, and this is actually a pretty intense question. So it has a lot of thinking that you must do. Okay, so I actually want to help you visualize this problem. Okay, so think about it. If I send an object like that, suppose this object is mass m. Now, must I really push it all the way to the moon or not? Okay, so imagine you have an object here. Must I push it all the way to reach the moon? The answer is actually no. Think about it. You only need to really push it towards the null point. Okay, why? Because the moment it passes the null point, right? Let's say this is the null point. Once it passes a bit, what happens is this fella will automatically fall to the moon already. Because the null point, right, is where the G field was 0. But the moment you inch past it, the moment you go past by a slight bit, actually the gravitational pull of the moon, G moon, is going to be very, very slightly bigger than G Earth, which means the object will naturally fall to the moon already. Okay, so yeah, this kind of question, very interesting, right? So what you do straight away is you say, okay, the mean energy, right, required is going to be the energy needed to reach the null point. Okay, and then here's the logic. Since after that, it will naturally fall to the moon. Because the G net will be towards the moon already. Okay, fantastic. So the minimum energy required is just this. I hope you agree, right? The mean energy is the gain in GPE. Okay, from where? From Earth to null point. Okay, then from there, right, the gain in GPE is just going to be GPE at the null point minus GPE at Earth. Okay, and then don't panic. Once you're done with this, wait, let me shrink this down. Need a bit of space. Okay. Once you reach this point, then I hope you agree this is the potential at the null point times the mass minus the potential at Earth times the mass. Okay, then look, you end up with this beauty, right? It's going to be phi null minus phi Earth bracket times m. Okay, and so what is phi null minus phi Earth? If you look at my picture, it's just going to be, you take whatever the value of phi null is, which is C, minus A. Okay, so then it'll be this. Minus C minus A times M. Okay, so whatever this change is. Okay, this is the delta phi. Right? Then times M. So you end up with A minus C times M. Okay, so this is the change in potential. Yeah, so this question, quite common. And remember, right, this is all given to you in exams. Like they'll give you the values. So don't panic about the calculations and what the hell is A and C. Relax, that one will be given to you in exam. Okay, yeah, so this is the minimum energy to push something to the other planet. Okay, so we're done with the mean energy to send it across. Now, what about the minimum energy, right, as it crashes to one particular planet? So it's a different question now. So let me copy and paste this diagram. One sec. Okay, let's do that here. Okay, then the question will typically ask like this. What is the minimum energy? And they'll specify the minimum KE that an object sent from somewhere to somewhere. Okay, what would the minimum KE be as it's sent from somewhere to somewhere else? Okay, let me write it this way. Minimum KE of an object crashing into the surface as it is sent from somewhere to somewhere. Again, and I'll make this question a little harder. So let's say it's sent from the moon to the Earth. Okay, so think about it this way. I'm trying to ask you this. Suppose, right, I have this mass here, this M, and I launch it from the surface of the moon, and I want to have the minimum energy, right, that this object will crash into Earth with. Okay, so actually, how do you think about this? Well, I'll give you some perspective. If you want the minimum energy, right, for this fella to reach Earth, it means that as you shot this fella, right, once he reached the null point, right, his speed must have been zero. Okay, so he was barely moving at this point, like almost zero. Then he had just enough energy, right, to tip over the null point. And as he tips over the null point, he flies and crashes into Earth. Okay, so then what energy does it gain as it falls from the null point to Earth? Then the principle is, well, you find the change in GPE. So from the null point all the way to Earth, you actually lost GPE. Okay, because your GPE was this value, right, was a high value, was a less negative value. And then as you drag that mass towards Earth, the potential just keeps dropping and becoming more and more and more negative. Okay? So yeah, that's the principle for this. So think of it this way. The object will lose GPE and gain KE. Okay? So then the minimum KE of the object is going to be equal to the loss in GPE. Okay, and in particular, right, I hope you agree with this, is going to be the GPE initial minus GPE final. Okay, and then the GPE initial, right, is just going to be GPE at null point minus GPE at Earth's surface. Okay, so we're only considering at the null point because the energy there was zero. The KE there was zero. And then as you crash over, right, you should get this GPE at null point minus GPE at Earth's surface, which is going to be a phi null times mass minus phi Earth times mass. Okay, and then I hope you realize, well, this is a M phi null minus phi Earth. Okay, yeah, so this was one of the harder concepts. Okay, so very quickly, let me cross this off. We are done with this. Okay, so then the last few parts are quite easy one. It's just about circular orbits in inverse square fields. Basically just satellites. Okay, so you must die know satellites. Let me see. So you need to know geostationary, you need to know gravitational force and its linked to centripetal acceleration. And also know how to solve these kind of questions. Okay, quite easy. Come, let's do that here. So let's consider this. Satellites. Okay, so satellites are just basically objects that are in orbit. Okay, and this one's quite intuitive. Let's consider this as Earth. So suppose you want to put some kind of satellite, right? So you can put the satellite here. Okay, so this is satellite. Then the idea is this satellite, right, will experience a gravitational force. Okay, like this, and it will circle around Earth. Okay, and the gravitational force, right, will obviously change. So like when I drag this satellite here, as it's orbiting Earth, the FG will be directed this way. It'll be pointing towards the center of Earth. Okay, and so whenever you solve a satellite question, the main strategy that you start off with, right, is you go and tell me what provides for the gravitational force. So the tip is this. Typically, just start with this statement. And they've become very strict over the years. So whenever you're solving satellite questions, right, you should start with this full worded sentence. Write this. Gravitational force provides for centripetal force. And I want to see this in full words. Because I think over the years, right, the teachers have gotten super strict about it. Like if you just write FG provides for FC, I've seen them penalized before. So some schools will penalize, others won't. To be extremely safe, just write it in full text like that. So gravitational force provides for centripetal force. Then from there, right after this line, then you can write this. Yeah, okay, so then quite easy. There's GMM over R squared equals to the FC. And there are three formulas for centripetal force. Okay, so let me color code them for you. These are the three formulas for centripetal force. So there's a mv squared over R. Okay, there's m omega squared R. And then there's also mv omega. Okay, so die must remember these. Okay, and yeah, I should also point this out lah. So if you want to do satellite questions, you should also definitely be revising circular motion. Okay, so yeah, this is how this is done. Okay, then I think yeah, another point that you must remember is this. So look at the top, they say this. So we're done with the first half already. So analyze circular orbits done. Okay, by relating gravitational force to centripetal acceleration. Okay, then I want to show you how this works. So the moment Fg provides for Fc, you can actually say this. Fg equals to Fc. And Fc, right, centripetal force is also the mass times the centripetal acceleration. Okay, and then isn't this also a m times the gravitational field strength? Then notice, right, that the gravitational field strength is the one that provides for centripetal acceleration. Okay, so notice when you're here, right, whatever g you're experiencing is also likely going to be the centripetal acceleration. Okay, so yeah, that's how they can test this. Okay, then I also realized they talk about inverse square law. Yeah, inverse square law is a very straightforward concept. So let me write that at the bottom. Okay, so what is the inverse square law? Okay, where is this? Okay, here. That's right. This. Okay, the inverse square law is a very simple concept. Basically appears many places in physics, whereby the gravitational force or any other force field, so it could be magnetic force, could be electric force also. Typically, these forces, right, are inversely related to r squared. Okay, so r is like the separation between the masses in this case. So they call it the inverse square law because the force of a force field is typically, right, inversely related to the square of the separation. Yeah, so that's how you can think of inverse square law. Okay, so yeah, we are fully done with this. Okay, yeah, and then finally, you need to know how to do Kepler's laws, satellite energies also. Okay, so for satellite energies, easy. Okay, so let me write it here. Okay, so consider this. Okay, so there are three types of energies for satellite. And pay attention, you must know how to do all three. So you must be able to derive from scratch. Three types of energy. The first energy, right, is GPE. Second energy is KE. The last energy is total energy. Okay, so I'll quickly consider this. So say this is Earth, and you want to consider a satellite. And a satellite, right, doesn't have to be like the conventional satellites that you think about. Like, you know, those that are used in telecommunications. It doesn't always have to be that. Anything that's orbiting the Earth is already considered a satellite. So you can even say the moon is a satellite to Earth. Okay, so like this. Then how do you even start thinking about the energies? But the easiest one to start off with is just GPE law. So suppose this is the separation between the centers of their masses. Then we can straight away say, oh, GPE is just going to be negative GMM over R. Then this one I just use the formula, can already. So done, tick. Okay, now next thing, how do you get the KE then? The KE one, right, is a bit tricky. So for the KE guy, let's consider this one. To derive KE, consider what provides for centripetal force. So the logic is, say this, Fg provides for Fc. Okay, and remember, right, usually we write the full thing. So gravitational force provides for centripetal force. Then from there, you can whack this. GMM over R squared equals to Fc, right? Now, within Fc, right, you have three choices. Recall, right, you have mv squared over R, m omega square R, and the last one, mv omega. Now, if I want to derive KE, it's actually super convenient to use this. So you whack that, mv squared over R. Now, avoid the temptation to cancel this m. Okay, why? Because you want KE, right? Because KE is half mv squared. So what you can do, right, simply just bring over the R, you get this. and then it's have mv squared, right? And then the idea is you're almost there already. You just need to times half. Okay, so I'll just times half here. That means I have 2r below. Okay, so then this is Ke, and this is GMM over 2r. Okay, so I'll write the Ke on the left now. So Ke is just GMM over 2r. And I'll box this up. Nice. So we're done with Ke. Final thing, total energy. So how do we get total energy here? Yeah, quite easy. So to get total energy, right, it's just going to be the sum of GPE plus Ke. Okay, and look, the GPE is just minus GMM over R. The Ke is just GMM over 2R. And then you get this, minus GMM over 2R. Okay, so this one also die must remember. Now, you might notice, what the hell? The total energy is negative. Does that make sense to you? And the answer is, it should make sense to you. We've discussed, right, when your total energy was 0. Now, and even now, you should think of it in nuclear also, nuclear and quantum. You guys must remember, right, that negative energy has a meaning. Negative energy just means that the system is bound, meaning the object, right, that's orbiting Earth is trapped there. It doesn't have enough energy to leave. So this negative energy makes a lot of sense. The total energy of a satellite is negative. Okay, let me write this here. Because it means that energy must be supplied to escape. Okay, so that's what this whole concept is about. So negative energy in this case makes perfect sense. Okay, so escape what? Escape the pull of the planet. Okay, so yeah, perfect. We are done with satellite energies. Let me take it here. One sec. Okay, so yeah, same. We'll go to the learning objective and cross it out. So done with satellite energies. Yeah, and then now finally, we also need to analyze Kepler's law and just tell you about geostationary orbits. Then we are 100% done. Okay, so what the hell are satellite energies? Sorry, what the hell is a geostationary orbit? Okay, so this is a fancy one, okay? And this one is specific to Earth. So consider Earth, right? It's like this. And now notice, right, actually the Earth rotates about its own axis. So in real life, the axis is like this. And then the Earth, okay, how I remember, right, which direction it rotates is it's the opposite of the sun. So how does the sun rotate? So is it west to east or east to west? So think, so sun rises where? In west or east? Okay, so remember, okay, actually, I don't know how you all remember this now, but in the army, we have songs for this. So I always remember it as from the song, right? Where the sun actually rises in the east and then it sets in the west. Okay, and so actually what's going on is the Earth is rotating, and basically, right, it appears that the sun is rising because the relative to the sun, right, the Earth is the one that's turning, and then it basically shines on the face of Earth. Okay, so yeah, the easiest way for you to visualize this is the Earth rotates from the east to the west. So it basically goes this way. This is the west to the east, right? Okay, so the sun appears to rise from the east and sets in the west, right? Which means that the Earth is the one that's actually rotating this way, from west to east. So take note, Earth rotates from west to east. Okay, so then look, if the sun was here, right? Then logically it appears as if it rises from the east and then sets in the west. So that's how you can remember it. Okay, so the Earth rotates from the west to east. Now, if you don't want to put all this hard info in your head, just memorize this. Okay, rotates from west to east. Okay, then yeah, from there, what the hell is geostationary? So geostationary means this. Suppose I have my satellite here. Let's call this a satellite. We call it geostationary if for any observer on Earth, right, somewhere here, it could be anywhere also, it's as if I'm just constantly able to look at the satellite, and relative to me, it doesn't appear to move. which means whenever the Earth rotates this way, the satellite also rotated in that same angular displacement. So like if I rotate by theta degrees, the satellite, right, will also have rotated theta, or rather traveled that theta, the arc, so that it matches this position. So basically moving with and along Earth. So to an observer, right, it appears as if it is not moving. Okay, so we can define it that way. Let me neaten this up. Okay, so you can say this. A geostationary orbit is an orbit where an observer on Earth views a satellite in this orbit to be stationary relative to his position on Earth. Okay, yeah, so that's what a geostationary orbit is. And then the logic from there is quite easy. So what are the conditions so that it appears to be stationary? And it's quite intuitive. We could say this. So what are the conditions? Firstly, well, how long does Earth take to make one full circle? The answer is 24 periods. 24 hours. Okay, so the period is 24 hours. Second thing, so apart from T being 24, you must also know that the satellite, right, must be directly above the equator. So you see the equator is here, right? Okay, that's the equator. It must be directly above the equator. Because if it's not above the equator, right, let's say it's above the like any random point, then even if the period is 24 hours, like that, right, because it will rotate around through the center of Earth, right, like that, it will rotate across, it won't appear stationary. So you want it to be directly above the equator, so it rotates with the Earth. Okay, so another condition for the geostationary orbit is it must be directly above the equator. Okay, and then the other thing is also quite common sense. It must also rotate from west to east. Okay, and how come? Because imagine if you obey 1 and 2, but your satellite rotate in the other direction. Then to a person here, right, obviously the satellite is moving, right? So that's why these are the three conditions. Okay, so other than knowing the conditions, you must also know this. Okay, so what are the advantages? So the first one is this, there's a constant line of sight to the Earth. Okay, so it's very useful for applications which require constant supervision over one area or constant line of sight for communications. Okay, so I can think of two cases. So nowadays the cameras have improved. So even though this is very far away, the logic is, if I, let's say, want to spy on one location, for example, you want to spy on a country that you think could be doing something bad, then you can plonk a satellite there and just monitor it 24 hours. Now, the biggest limitation to that in the past was that this distance is so freaking far away that these kind of satellites, right, are not very clear, not very HD. So actually, it's more likely the case that in human applications, the usefulness, right, is if this was always communicating. So like, let's say this is a telecom satellite. So for example, it could be like Singtel satellite. Then it's always directly above Singapore, for example. Let's say this is SG. So there's a constant comms between them and it's never interrupted. Yeah, so that's why these kind of satellites are useful. They are called geostationary satellites. Okay, so if you want more info about this, you can find it in the notes as well. Okay, so done with this learning objective. Okay, yeah, then the last thing we need to cover, is Kepler's law. Now, Kepler's law is out of the syllabus, but they always ask you to prove one. Okay, so they won't tell you it's Kepler's law, but if you do enough questions, you will have seen this a lot. So Kepler's law goes this way. T squared proportional to R cubed. Yeah. So they're trying to say this. The period of a satellite or an orbit is proportional. Okay, let me write this out. Square of period. Proportional to the cube of the separation. Okay, or let me just write it as the orbital distance. That's the easiest way to think of it. Okay, then this one quite easy. So I can prove this out for you. So must be able to prove. Okay, so consider something like Earth here. And then consider this as your satellite. Okay, so the logic is, can you prove that the period of this orbit, right, is going to be proportional to the R here? Okay, and then you probably already can guess, for this kind of stupid satellite questions, right, just start with this one. Gravitational force provides for Fc. Okay, and then, yeah, I should write it in full, sorry, centripetal force. Okay, so I'll do it like this. Fg equals Fc. Okay, and then straight away GMM over R squared is going to be Fc. Now remember, right, you got three formulas for Fc. And if I want to prove the period one out, okay, so you have three to choose from. It's mv squared over R, m omega squared R, and mv omega. Then the one to use, right, is actually this fellow. Now why? Because the omega, right, is 2 pi over t. I can go and get this one. Okay, so that's why I want to use this fella. And why don't we use this? Okay, because usually they don't give you the velocity. Okay? So typically when you're solving this, right, you just use this equation. Okay, and so then you get something like this. M omega square R. Okay, then from there, M 2 pi over T square R. Then this is GMM over R square. Okay, so you basically make T square the subject. So let me do that. Okay, let me cross out the M first. And then bring everything to one side, basically. So T square equals to, let me bring this up to the left. So you get 2 pi R over GM. Then you have R square brought out also, so it's R cubed. Okay, yeah. So then notice this. Okay, so therefore T square proportional to R cubed. Okay, so yeah, Kepler's law is done. Okay. Okay, then finally, this last part, right? You need to also know how to use proportions to solve questions. Now I'll go through one common thing on how to solve this kind of proportions questions. So this one, right, highly encourage that you do this worksheet. Is the H2 gravitations worksheet. And dude, they test like crazy one. Yeah, so they love to test this stupid shit. And the one I've seen so much, right, is when they force you to push in density inside. Okay, so give me a sec. Let me find one question. It's one about the density. Okay, hold up. Okay, yeah, this one example. Okay. So you need to be able to solve questions which require proportions. And I have an additional worksheet on this. I'm gonna send it to the class real soon. But for now, let me just show you what I mean by using proportions to solve this. Okay, so let's start off with this. Okay, so there's actually two things that you should do. Using proportions to solve questions. And then knowing how to force in variables. Okay, so I'll give you an example here. Okay, so if you are done or okay, you should pause the video and then try it and then play the video once you're done. Okay, so I'm assuming you've paused it already and ready to start now. Okay, so this is how I would tackle the question. First, they tell you, right, that they want you to go and find the ratio of the radius of planet X to planet Y. And then they tell you about the acceleration due to gravity on the surface of the planet. Okay, then they tell you that they have the density also. Okay, so what I mean by the second objective, right, is you need to know that you need to force in certain variables. And then after that, you want to use proportion to solve the question. So I know, right, eventually I need to find the ratio of X to Y. Okay, and then they already tell me the comparison, right, of the acceleration of X compared to Y. So how do I even start solving it? Well, don't try to jump into the proportion straight away. Instead, right, force in the variable first, which means they give you density, right? So you try to force in the density first. And they also give you acceleration, right? So you force in density and acceleration. And naturally, right, if you do things right, the last thing will appear, which is the radius. Okay, so here was my thought process. So step one, which is this. Step A is this. Force in the variables to come up with an equation first. Then step two is apply proportions. Solve for the desired ratio. Okay, so yeah, that's how you can handle this. So in this case, I'm actually going to start looking at forcing in the variable of density, which is here, into the acceleration formula. Okay, so that is step A. So let's do that now. So notice they give you acceleration due to gravity on the surface. I hope you agree, right? Acceleration due to gravity is the G field strength. Okay, so immediately, okay, I know I need to start off by coming up with some equation. So that's this. You say G is going to be Gm over R squared. Okay, and look, I want density. So I'm thinking in my head, right? How do I force in density? Now, the easiest and nicest way to do this is to think of how to force in mass over volume. Okay, and so you know it's a planet. So the planet's volume, V, is 4 over 3 pi r cubed. Okay? So I just want to make it very nice, right, for me to put in density into this equation. So notice, right, I just need to force out the volume to be at the denominator. So then I'm thinking in my head, okay, this is mass, and then the volume is 4 over 3 pi r cubed. Correct? So look, I hope you can see the pattern. I already have m, I already have r squared. I just need to make the denominator this 4 over 3 pi r cubed. So easy lah. Okay, what you need to do next is, on the top right, you don't need to do anything special. But at the bottom, you need to times 4 over 3 pi r. Okay, so you want to times 4 over 3 pi r, so it becomes 4 over 3 pi r cubed. But since you times the denominator, right, you must also times the numerator. Okay, and to show you why, right, because, okay, let me write it with one more line. I hope this makes sense to you. Okay, I'll drag this down, and I'll say, okay, it's here. And this is times 1. Right, so G is Gm over R squared times 1, right? And I change the 1 into this. And then look, notice, right? When I push this in, it'll be this Gm times 4 over 3 pi times R. And then at the bottom, I have this lovely expression, 4 over 3 pi R cubed. What the hell is this? This is volume already, ma. So I hope you agree with this. Okay, notice, right? I've grouped this together. Right, so m over 4 over 3 pi r cubed is m over v. Okay, and if you can see already, mass over volume, very nice. This is density. Okay, that's that. So that is G. Okay, fantastic. Now you got this equation. Step A over already. Okay, then step B, you just need to apply proportions to this. Okay, so they're telling you, right, that you have the acceleration of gravity on X being 3 times that on Y. So actually, right, you can straight away just whack this on. Gx over Gy is gonna be 3. Okay, and look, you might want to suck the whole thing in, but that's so ugly. Don't do that. Use proportions. Now, remember, for proportions, right, you're basically saying that I want to disregard the constants because they're gonna cancel off anyway. So, in other words, only look at those that are non-constant. Okay, so I hope you agree. 4 over 3 is a constant. Pi is a constant. G is a constant. So actually, right, the proportion that we're trying to abuse is this. G is proportional to density times R. Nice. Now that you have this, plug it in. So notice, right, if I want the gravitational field strength of X, it's going to be the density of X times the radius of X over the density of Y times the radius of Y. Okay. Wow, that was a lot. Okay, and then you're done. So now that you reach here, time to celebrate already. You just need to sub in. Right? So look, G of X 3 times of Y. So then we can say this is 3 over 1. Okay, and then you also have the density being the same. Right? So same mean density. So that means I can say rho X on rho Y this value is equals to 1. Okay, and so like I mentioned, we are done applying proportions. Then you solve for the desired ratio. So they just now ask you what's the radius of x to y. Okay, so let's see, radius of x to y. What the hell, it's just 3 to 1. We are done. Cheers. So the answer is C. Okay, so yeah, I will give you guys a proportions worksheet. I'll make it self-practice because it's quite intuitive. Okay, and then congrats, you're fully done your revision for gravitation. Now, bear in mind, right, that this is just a revision for the concepts. You still really need to grind a lot of questions. Okay, so done with this. Okay, see you guys in the next video. I haven't yet done the analogy between G fields and E fields, but I'll leave it after we done a revision on E fields also. Then I can really connect the dots. Oh, actually, you know what? I got one last thing I want you to remember. Then that's it. Okay, so the last thing is the 4 boxes. Okay, so you have to remember the 4 boxes. Okay, so the 4 boxes, right, is telling you the relationship between certain important gravitational variables. So stuff like this and this. Okay, then the first one is gravitational force. Okay, then the second one is gonna be gravitational field strength. The third box is gonna be GPE, and the last box is gonna be phi. Okay, so I think quite easy. In my head, right, the way I always remember it, right, is this energy, right? It's like work done. Then work done is basically area under force distance graph. Okay, so I hope this makes sense because you can also say work done is basically a integral of force. Okay? Yeah, then wow, it becomes very easy from there. So you see, right, you got energy here, then you got force here. So if I want to go from force to energy, I basically just integrate. Now, there's always this negative sign, okay? And this negative sign appears because remember, right, that we define GPE as the work done by an external agent. So that's why there's always the opposite direction to the gravitational force. Okay? So yeah, that's it. So minus integral dr. Then this side, right, is just the opposite. So it's minus d over dr. Okay, then same thing here, divide by mass times mass. Okay, so from Fg to go to G, I just divide by mass. From G to go back to F, I times mass. Then basically this, right, will apply to the bottom row. This will apply to this side also. Which means, okay, if I were to really show it again, it's the same thing. So to go from G, right, to phi, I'm going from field strength to potential. I integrate. Okay, and then to go from potential to G, I must differentiate. Okay, then now here, from here to here, divide by M. From here up, times M. Okay, yeah, if not, that's all already. Okay, so go and grind the questions. Good luck.